Hi, welcome back to the breadboard. Been neglecting my duties recently regarding actually doing stuff with breadboards and components and things like that, so thought I'd remedy that. In the last tutorial video, we started looking at driving components, specifically LEDs. We drove LED like this. We also had red LEDs and various other ones. Showed you how to do dimming and things like that. What I have laid out in front of you is effectively the next step in evolution. These three active displays, this one here that's slowly counting across 1, 2, 3, 4, is directly coupled to an Arduino Uno, and this is basically 4 digits of 7-segment LEDs, and each one actually has a decimal point LED as well. But fundamentally, it's exactly the same as one of these. I'm going to turn the light back on now so that you can see things a little clearer. I wanted to let you see this display too, which we'll cover in a second. Okay, that's a little better. So yeah, all of these LED displays are basically fundamentally one of these, just lots of them. So these 7-segment displays like this one here, they are made up of just 7-segment displays in one package, and these are basically just 7 LEDs, well 8 because they have this decimal point as well. So 7-segment with decimal point displays, and what they are, as I said, is 7 or 8 of these LEDs with the cathodes all common together. So you would ground one end and you'd provide power to the other end. So what I have on here, and we'll look at the code in a moment, is an Arduino Uno with 7 of its outputs connected to the A, B, C, D, E, F, G segments of the 7-segment display, and 4 of the outputs driving the common cathode. So it's high, it'll be off, and it's low, it'll be on. Or is it the other way around? Sorry, other way. And I've got an extra long delay in so that you can see what it does to scan the display. What we have here, I just take the cover off. The red filter makes it much easier to see things like this. Is 1, 2, 3, 4 of these kind of displays in series. Well, if you look at this, you've got 7 wires, 8, 9, 10. You've basically got 10 wires used here just to drive one display, right? Here, if you discount the power wires, we've only got 3 wires, and we're driving 4, 8, 12, 16 digits, which would require far more I/O than what this Arduino Uno has in order to drive it. Or if you drive it in a multiplexing way, you would have to have, well, we've got 16 digits, so we'd need a driver common for each of those 16 digits, plus the 8, so we'd need 24 wires just to be able to drive this display, and we'd have to be scanning them like we're doing here very, very quickly so that you can make up the numbers and things that you're trying to put on them. Because what's happening is that in this case, it's going slowly to scan, as you can see. But on this one, these are actually being scanned one at a time so that you use less power. And also because you can only have 1 digit on at a time on each of these displays, because all of the anodes are, common cathode, all of the cathodes are connected together. So you can't just put a number you want by energizing A, B, C, D, E, F, G, so that would put an 8 up, and then have all of the common cathodes connected to ground to turn it on, because they would all say the exact same thing. So you have to go 1 digit at a time, changing the data on the anodes. You can get these in common cathode and common anode, and then scan across to make up the digits, which is exactly what this one is doing. We'll look at the code in a minute. So when you start expanding these out, or maybe you wanted several rows of something like this, what do? Well, the answer is exactly what these boards are doing. They have a serial to parallel effectively converter. It's got a decoder in it which you can communicate using the SPI interface, that's SPI, Serial Peripheral Interface, of an Arduino Uno or of pretty much any microcontroller. Talk to the chip that is behind these displays. Actually, if I just pull one off, I can show you. On the back, you see you've got this chip here. It's a 24-pin chip, and it's designed to drive a 7-segment, 8-digit display. One of these displays, so that ends up, if you ignore the decimal point, no, if you include the decimal points, you've got 64 LEDs in there. This also has 64 LEDs. They're just arranged differently on the panel. And you can see, right, they've got this, in this case, they've got 8x8 wires coming out the back so that you can scan any individual one, but you'd have to have a rat's nest a bit like what you've got here in order to do it. This one has, guess what, tucked in behind. It's a slightly physically smaller one, but it has one of those driver chips as well. So again, using a SPI interface, so power, ground, and 3 control wires, you can address any one of the digits on this display in the same way as these are being driven. So let's have a look at the code for a moment. I've got a few code examples here first. Let's go in here. So this is the, let's change to the code view. Okay, so this is the 7-segment display code that's running on the Arduino Uno right now. They're both Arduino Unos, aren't they? It's the one running on here, driving this little 4-digit 7-segment display. So what we've got here, without going into too much detail of individual commands, little picture showing you the segments. So A is the top digit, B, C, D, E, F, G. And if you look at the data sheets, all the chips could have various pin outs. You can find out which pin goes to what within the display module. First thing the code does is we define all what the pins are going to be. So these are the segment pins, A, B, C, D, E, F, G, which is the way that they are standardly labeled here. So if you wanted a 0, you would turn on A, B, C, D, E, F, and not G. If you wanted 8, you would include G. If you wanted a 1 on, just B and C would be turned on, or F and E. If you wanted a 2, you'd have A, B, G, E, and D turned on, right? For an example. So what do we do? So we've done that. We've set all these outputs. We're using, it's not the best practice what I'm doing right now with it, but the chips are reasonably self-limiting for a certain amount of time. D1, 2, 3, 4, which are the digit selects, are also connected to outputs of the Arduino Uno. So it's going to limit the current to about 30 milliamps on that pin at absolute max. So these are not quite as potentially bright as they can be. And if I was scanning this at full speed, it really would be fine, because they would only ever be on for a very, very short period of time, so things wouldn't overheat. So that's our setup. In the loop, we write to the digit pins which digit we want to light up. So in this case, it's digit 1 is the first one, 2, 3, and 4 are low, so we're not providing any volts into that. And then we write to the segment display, which is, in this case, everything is on except for pin G. Remember, high on the input to the common cathode, sorry. Right. And then the other end has to be low to turn on the LED. So we've got all of these low and 1 off, so we get a 0 in the first digit, which is what you saw. I delay 1,000 milliseconds, so I wait for a second, and then I switch the second digit, and I very quickly change the second digit output to draw a 1, in which case only pins B and C are turned on. I then wait a second and switch to the next digit, which turns off the previous one, of course, and turns on the next one. And I then write a number 2, which is basically just turning off pins C and pins F. And then I just do a digit 3, and then I repeat the loop. So if I just change this code slightly and make this a 1 millisecond delay instead, Now, if I switch, I'm going to compile and upload it, but I want you to see what's happening when I do it. So there's a closer view. Let's just get this into view here. Okay, you can see it's running slow. And what I'm going to do is compile and upload. Should see the lights here flicker in a second. There we go. Now, these, you can't tell that they're scanning. If I go back to the I'm on the display, you can't see it very well there. If I put a filter in front, you can see. Now there's no, hopefully the camera's not picking it up. I'm not seeing it here. You can see there's no flicker at all now, and that's what you would normally do. Now, these displays here are doing that exact same thing. The only difference is, instead of the Arduino Uno being told, change this pin, change this pin, change this pin, it's talking to Max 7219 controller chip. This is the datasheet from Maxim integrated for it. And it can drive these using SPI. All the information's in here. I'm not going to go into a great huge amount of detail. But aside from power, as I said, it does allow you to control way more with just 3 wires. Now I can extend this display to have, I think 8 of these modules. So 8 digits times 8, that will be 64 digits in total, which is pretty impressive. And you're not using any more wires from your computer. Now, you can, I'll provide a link to this panel, but here's, this data sheet. Here is the basic overview here. You've got your microcontroller, which is in this case an Arduino Uno, sending data in serially. And you've got 8 wires coming out of this chip to drive the data lines, and you've got 8 wires coming out to select the different segments. In the Uno program we were looking at initially, we were only using 4 digits. In this case, this chip is capable of driving 8 digits, and we can have 8 of these modules serially connected between each other. So it works quite nicely to do that, like we've got here. Now this is just running through a program. It's a little bit more advanced programming. This one is more in line with beginning tutorials. I will be covering the SPI interface in a future video, which will come out hopefully soon. Now the last display that I've got here that I'm showing is this one here, which seems to be a very, very complex display. And what this one is literally, I was going to say 512 LEDs. But seeing as every single of one of those 512 LEDs is an RGB, and we've seen one of those in my earlier videos, then technically it's 512, 1024, plus another 512, so a little bit over 1600 LEDs in here. And you can vary the brightness on them. Oh, you can do that also on these displays too. Just here, you can tell the controller how bright to make them, which is a nice feature. These ones you can do the same as well by using pulse width modulation techniques and things like that. But this one is a little bit more complicated, and an Arduino Uno really is not powerful enough to drive something like this. Certainly not if you wanted to do something else with it as well. So what's driving this one is actually an ESP8266. It's got more memory and it's got more speed in here. So an Arduino Uno is an ATmega 328. It runs at 16 megahertz and it has very little memory in it. The ESP8266 has an external memory chip that has well over a megabyte of flash. In fact, you can get up to 4 megabytes in them. It's running at either 80 odd megahertz or 160 megahertz. You can program that. And again, it's using shift registers to support it. If I go on the back of this, you can see these are all shift registers. So it's sending in RGB data times 2 because it's effectively 2 rows on the front. And they're shifting through. These are effectively the same kind of thing as what's driving these here. They're a little bit different, but they're serial to parallel shift registers. So you serialize your data in, it shoves through all of these, and you do it twice. You've got 2 sets of them, but then you have to multiplex the rows. So you're actually writing to 2 rows at a time and selecting which columns. So you're writing the data, say, to the first row and the 9th row. You serialize it out. Then you select the next row and you serialize it out. And then you select the next row and you serialize it out. And you have to do this very, very quickly. Very much the same as we're multiplexing this display and we're multiplexing this display. This is going way, way further where you've got, right, so there's 8 of the LEDs in one row. So you've got this little corner, which is already 3 times as many LEDs as what's in here. And we're doing this big display. And you can daisy chain these together as well, as long as you've got a fast enough microcontroller to be able to drive them. But why I'm showing you this right now is because I don't want you to think that just because you have a small microcontroller, and even an ESP8266 is a very low cost small microcontroller, you're able to do some very cool things with it and not take up too much data. This one's able to probably run the Wi-Fi as well while it's doing this, so you could probably send it different commands to put different things on the display. I just have a test pattern right now. We're going to do a separate video on this as well, driving these types of displays. I have a few different kinds. Anyway, I don't want to go into any more detail on that. The other thing I want to have a quick look is what this display code is doing. All right, we've had a look at this one. So let me just bring up my Arduino. So to continue the discussion regarding the 8-digit 7-segment displays that you can daisy chain, remember they're using the SPI interface from the microcontroller, and we're able to send out as much data as we need. The MAX 7219 chips that are included on these boards are daisy chainable as well, and so you could put 8 digits, 16, multiples of 8 digits on up to 64 digits in total, which could make quite a nice display for, say, a dual output power supply, some kind of motor controller where you're showing the RPM, temperature, and things like that. Quite a lot, it's up to your imagination what you're going to do with it. But the point is here that I'm trying to show, without going into too much detail on I2C and things right now, is that with smaller microcontrollers like the ATmega 328, which is the one that's used on the Arduino Unos, you're not limited to simply the number of pins that are on the Arduino. In my first example, where I had the software driving directly the digits of the 7-segment display, which is like this one right here, it took a reasonable amount of code. If I just look at that in the IDE from when it compiled, just bring it up. It used 1,296 bytes, so 1.2K of program space, and it's only got 32K in total. If I started trying to do what I was doing on the extended digits, it would be taking a lot more code. Now, there's no libraries involved on this one. All I'm doing is direct pin manipulation. So it would also be taking a lot more of the processor utilization to do what it's doing. If I look at the code that is running on out to the MAX 7219s, it's using 3.3K, so it's using almost 3 times as much code space. The difference being, though, actually, it's 4%, now it's 10%, so it's about 2.5 times. If I want to start doing a lot more, this is not going to increase, because I've included, the reason why that's grown so big is because I've included the SPI library, which is used to drive the serial interfaces of the controller. I've also included a digit-led 72xx.h library, which gives me a whole bunch of functionality for the 7219 chip, allowing me to output characters 0 through 9, H, E, L, P, and a dash, and of course the dot. These are all the standard supported characters. Obviously, you can do things like A, B, C, D, E, F with the display, but you would just bit bang those sorry, I wouldn't say bit bang, but output them as a bit pattern so that you can directly control the specific segments to get those characters. But all of that is normally taken care of by the library. When we go through the SPI, I'll make sure that we specifically look at what you can do with this library as well. The underlying thing here, though, is that it simplifies your coding. You're no longer worrying about how you physically drive the 7-segment displays. It's gone. You need to know what pins you're using. You configure it once, and then you basically forget about it. And you can see here, we've got the library. We define the load pin for the chip. We tell it how many chips we've got, and then basically, we initialize it, tell it what pins we've got. After that, it's just using the library. So we've got things like LD for the display. That's how we've declared this, the digit LED. On, and then 2. The 2 is telling it how many chips there are, and then we're telling it LD print digit 76543210, wait a half a second, print, and then we're printing this on the second segment, 4321. I don't know if I can actually increase that and have it go on both of them. We then start doing a loop, so that's doing this on the initialization. In the loop, it's just doing print 1 2 3 4 5 6 7 8, wait a little bit, clear the display, print, clear, different things, of course. We've got a negative sign in front of the 2222s. Now we've got some counting just to one of the displays. Now we're doing the counting to both the displays. I think in this one here, yeah, we're using the N. Right, so we're doing a number of different things. This is where I think it's doing the little bouncy square thing in the display, and then it's clearing it, and then it's looping through the whole thing again. The ++N is just incrementing the display that we're selecting to do things on. So if we look at what is in, I'm not sure how easy, I think I can do it in this. I'm using in this particular instance, I'm using the Arduino IDE version 2 beta, and one of the things it has is Intellisense, like right here. So if we go into the print digit, you can see you've got a long number that we can provide it to. The device we're writing it to, and the start digit. So note there are only a few characters that make sense here. So 0 1 2 3 4 5 6 7 8 9. End device, the address of the display. So that's which display. The start digit. So you don't have to print on the left side of the display. You could start printing somewhere in the middle. Value to be displayed. And where you want to put the decimal point. All right, so it's very, very straightforward, but it hides all of the physical functionality from you. And you can display a digit, or you can, where is it? There's somewhere else here. Oh, here. Here we are writing to the display. We're telling it which character. If I go over the right here, you can see you've got the address, the data, and the device. Okay, and what that we're doing here is we're saying write to this particular digit, so in this case digit 5, and we're telling it to write out this binary pattern, which is segment A, B, C, D, E, F, G in the decimal point, and then the display to write it onto. Right, and then it's changing the pattern here and going through. So if we actually look at the display for a moment, so here's the little digital write ld.write function. It's just changing the character there. And now we've flipped over to the other display. So if I just hit reset, right, so you can see that startup sequence that was in the setup, and now it's gone into the counting mode. So I don't want to waste too much more time in this specific video, because this is really just continuing the, if you like, education path. I will provide links to this code. I think I'll put it on my website, and then you can download it if you want to. So this code that was driving the SPI-based Mac 7219, I didn't write it. I just downloaded the library, and it's part of it from this guy, Leonardo. So it's very simple. It's quite well commented, works very well. The code that I wrote was this one. I did find some in the library, but it didn't work for my particular display. And I also cleaned it up so that it made it very easy to switch between common cathode and common anode displays. Just by changing this up here, if you want to have digit on is the common side is the plus voltage side of the display, or the common side is the negative side of the display, you can just change this digit on to a low or a high depending on what you have, and then the segment on is always typically the opposite of what the digit on is. So you provide a plus voltage to the common side, and then you ground the individual segments, or you drive the individual segments and you would provide a ground from the digit on. Now all you've got to do is, if you change that from a high to a low, it'll either be running as a common anode or a common cathode. So if you try one and it gives you all sorts of weird things, flip that from a high to a low and it should flip it around. All the segment definitions are the same. These are the pins that you plug your wires into as well on the Arduino Uno. If you want to slow the whole things down so that you can see how it's working, just change this digit delay from 1 to say 1,000. That will give you 1 second between each one. You can see it driving each individual display. The bit patterns are a little easier to see from what I originally showed at the beginning of the video. It's just digit on, off, 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 and then segment on and off for each of the individual segments, A through G. And then you just go through what you want on the 4 digits. So that should work pretty well for you, and I'll post this code as well so that you can download it. Okay, so if we look at what we have right here, we're going quite quickly right now. If I change this to, in the code, let's go back to the code here. If I change this delay to 1000, and then just upload it again, just compiling, uploading. Okay, now you can see it's going slowly again. All right, makes it quite easy to understand. And if I wanted to I don't have the decimal points connected up in this particular instance, so that's fine. So that's showing us what we want to be able to do here. Okay, so in summary, what I've taken you from is driving an individual LED up to driving 7-segment display. So that makes it much, much more useful. These advanced displays, like these 7-segment ones and this matrix display, we'll cover in future videos. But for now, this should be enough for getting you going driving one of these displays. And you get these displays in almost every single Arduino kit that I've seen. So you can easily set up your own. But they take, each segment is taking about 30 milliamps. So if you were driving this on batteries, you would have to have a big enough battery that's going to keep the going to last a reasonable amount of time. What I have come in the mail to me is some displays that work very, very similar to these. They're 7-segment displays, etc., etc. But there's a variation that are actually printed onto plastic, basically, and they take nanoamps, if that, to even run. They're a little bit like e-paper. Once you set them up, they can remain on the display for a little while, but you can easily drive them from 3.3 volt logic and things like that. They work very similarly, and I want to show you in the next video. And I want to show you in the next video how to use those. Coding shouldn't be any more complicated than this, or at least not much more complicated. And it should be quite interesting, and it will show you how to do a very similar piece of functionality, but with something that's going to take a fraction of the power. We will be continuing these lower level tutorials building up to using keyboards and things like that. I have some, actually, where is it? I put it down somewhere. Let me just grab it. So yeah, we got some keyboards like this, which, I mean, you can get different kinds with different prints on, but basically it's a 4x4 keyboard. It's very similar in a lot of ways to this, but only this LED display is an 8x8 and it's driving LEDs. In this case, it's a 4x4 and we're reading from little tactile switch buttons. Right, so we'll go through very soon on how to drive, or well, read from these, how to scan them and read from the keyboard and use it in a program. And then we'll go on to combine the two and things like that. So that's it. If you like the video, give it a thumbs up. If you don't, then you don't have to, but it's always appreciated. Having said that, I will see you in the next video. Bye for now.